Okay, so we've covered everything for the next exam, so I figured we'd start with some review problems. So here we have a mechanism problem. When epoxide A is treated with methyl magnesium bromide followed by a mild acid workup step, a bit of compound B is formed as a byproduct. Draw the mechanism. Okay, so this is a byproduct. It's not the major product, it's just a byproduct. I'm trying to figure out what went on here. If we take a look, compound B has quite a few carbons. Compound A has 1, 2, 3 carbons. Compound B has 6 carbons. Actually, 7 carbons. Makes it worse. So, first thing to do, you can try to figure out the carbon situation. You can also start by going with what you know. Methyl magnesium bromide. That's a Grignard. What you see Grignards do is they act as bases, and they also act as nucleophiles to epoxides. And that nucleophile adds to the less hindered side of the epoxide. It's an irreversible step, giving this. Now if we take a look at this molecule here appears in the product. But we still need more carbons. Well, remember, you never have just one of a molecule in a reaction. You have several million molecules, billions of molecules. That means you have an additional epoxide. You have an O-. An O- can react with an epoxide. It attacks at the less hindered side. Like so. And this is compound B, except we're missing a proton. We just need to protonate it. Like so. Now, the question also asks you to examine the bond going to the methyl group with an asterisk. Should this bond be a wedge or a dash? Well, what's asking for is what's this chiral center right here. That chiral center was never attacked, so it should have remained the same throughout the entire process. That carbon right there, this carbon, 1, 2, 3, it's an S chiral center. And so in order for this molecule up here to be an S chiral center, that's 1, that's 2, that's 3. The hydrogen has to be a wedge coming towards you. That means the methyl group, therefore, needs to be a dash. Okay. Okay, next one. Next one is a synthesis problem. Write an efficient synthesis of the target molecule from the indicated starting material. Well, there's two ways of approaching this. You can either start at the beginning, the starting material, and go forwards. And I suggest you only do that if you see an easy way of going from A to B. If you don't see an easy way of going from A to B, I suggest that you forget about the starting material and just focus on the product itself. We have a Br and an OH. They're anti to each other. We have one reaction that puts bromine and water anti to each other. That's adding Br2 and water to an alkene. And the OH goes on the more substituted side, like so. Then we take a look at our starting material. Starting material, if you see an easy way of going from there to there, then do it. If not, forget about that. Just focus on the product right here. How do you make that? Well, that alkene is made by elimination reactions. We can eliminate a bromide from there, or we can eliminate a bromide from here using a base. Now, in the first case, we don't have to worry about chiral centers and stereochemistry. The second case, we do because of the anti-coplanar rule. If this bromine is a wedge, that hydrogen needs to be a dash. And then we take a look at our starting material once again, what we're trying to get back to. And we see that we may not be able to find an easy way of going from there to there, but we do have a way of going from there to there, and that's simply just adding HBr. Like so. Other things you could have done is you could, since this is the more substitute alkene, we could have used sulfuric acid and done an E1 reaction on an alcohol. Then that alcohol can be made by using catalytic amount of acid and water, since it's a tertiary alcohol. Or you could have used oxymercuration, followed by demercuration. So that's a possibility as well. So either route is fine. Acid-base reactions. For each of the three molecules, rank them in terms of basicity. The strongest base is 1 and the weakest base is 3. Okay, so let's take a look at these molecules. First thing I suggest you do is you look for any lithiums, potassiums, or sodiums, and you get rid of them. On the last quiz, a lot of people drew in the sodium on that acetylide, and then they drew absolutely awful mechanisms. Please, 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 just get rid of it and replace it with a negative charge. So much better. And so here, this molecule here has a lithium, so it's best to think of this molecule as this. That's it. Now we're talking about basicity. So basicity is looking at the conjugate pKa's. So the conjugate acid of this molecule is here. The conjugate acid of that amine, of the amide, is here. And the conjugate acid of that alkoxide is here. This has a pKa of 10. This has a pKa of 35. And this has a pKa of 15. We're looking at the strongest base. The stronger the base, the weaker the conjugate acid is. So this is the weakest conjugate acid, making this the strongest base, followed by this one, followed by this one. Now it says to circle the bases that react irreversibly with water. Well, water has a pKa roughly around 15. When you get to the irreversible reactions, that's 10 and higher. So you need to circle anything that's greater than 10 of this. So pKa's greater than or equal to 26, you need to circle. If you circle a pKa of 25, that's okay. It's all good. But you definitely need to circle everything with a pKa, or I should say conjugate pKa, of 26 and higher, because those will react irreversibly with water. How can you tell? This plus water gives this pKa of 15, pKa of 35. There's no backwards reaction. This reacted irreversibly with water. Look at the other way. pKa of 15, pKa of 15. This can react with water, but it does not do so irreversibly. And so on and so forth. Okay. We look on the other side of the scale, chloride, water, here's an example of an irreversible reaction, because this has a pKa of 15, and this has a pKa of -5. It's definitely irreversible, but it's going the wrong way. This chloride does not react with water, because the arrow isn't going away from it. Here, this alkoxide reacts with water, but does so reversibly. Here, this amide reacts with water and does so irreversibly. So that's what I mean by this. Okay, drawing the missing reactants. Okay, so here we have a molecule of this alkene given to this diol. Well, we have two ways of adding two OHs across an alkene. One way is MCPBA followed by sodium hydroxide and water. So that's an epoxidation following opening. This gives anti. The other way is osmium tetroxide and NMO. That gives syn. Problem is, don't know which one this is, syn or anti. But we do have some clues. If we take a look at the arrangement of this, we have the cyclopentane, like so. What we need to do is redraw this molecule so this methyl group and this cyclopentane match this curve. See that? Just like that. If we do so, if we redraw the molecule like that, the OH would be a wedge. And this OH is also a wedge, because we didn't rotate that part. And so if you take a look, these OHs are both wedges. That means we need osmium tetroxide NMO. Now, you could have redrawn the molecule like that, where the two methyl groups are trans to each other. In that case, you redraw the molecule like this. You do so, that OH still is a wedge. And if this methyl group, you wanted to have that as a line going upwards, that means this OH is a wedge going up, going to the bottom of the page. And then that means that cyclopentane is a dash. If we take a look, two OHs, both wedges, syn. It's osmium tetroxide NMO. If one was ended up being a wedge, one ended up being a dash, then it would be the anti. Okay, methyl magnesium bromide. Well, this reagent we have works with epoxides. Adds methyl groups to epoxides. And it does so when you add a nucleophile to the epoxide, you get this pattern where the nucleophile is attached to the beta carbon. Here's the alpha carbon, here's the beta carbon. We have two methyl groups possible. So let's figure out which one. If we go with the red methyl group, here is the alcohol we would use. And so to get this, we would have this epoxide. That's with the red one. If we did the blue one, we would need to redraw the molecule like this. In that case, the epoxide then would be this one. Which one? It turns out the blue one is the correct answer. The red one will not work. The reason why the red one will not work is if you take a look, there's something else that's optically active. In order to have an optically active product, a starting material must be optically active. The blue one is chiral. It can be optically active. The red one is achiral. It cannot be optically active. So if you react the methyl magnesium bromide with the red one, you would end up with a racemic product. You'd end up with both enantiomers. You can attack both sides. If you react methyl magnesium bromide with the blue one, it can still attack both sides, but it doesn't matter which side you attack, you get the same enantiomer out of it. So the answer does involve that blue one. So that one, incredibly challenging question. So we have copper cyanide, ether, and this epoxide, which must be optically active. Followed by H3O plus, the acid workup step. Yeah. Very, very tricky question. Okay, C. Take a look at C. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What we've done is we've broken the carbon-carbon double bond there, made an alkene. Well, we have lots of different ways of doing that. One way is ozonolysis followed by a reductive workup. So that could be triphenylphosphine, or dimethyl sulfide, or zinc and acetic acid. Any of these three, because you have aldehydes. Or you could do osmium tetroxide followed by pyritic acid. That's an option. Third option is pyritic acid can also cleave anti-1,2-diols. So you could add the two OHs anti to each other and treat with that. So, three possibilities. This one here, an alkene, adding a Br and an OH. Well, I guess this is kind of a repeat of the earlier problem. We just have one thing that can do that. Bromine and water. The OH goes on the more substituted side. The bromine goes on the less hindered side. Okay. Have a little time left. So I want to talk about the quiz. Give me a moment. I will draw that quiz problem up. Okay. Quiz. Okay. So, the quiz. You take this alkene, and 3 steps later, you have an alcohol and an alkyne attached to it. So, first thing that happens is in bromination reactions, you form the bromonium ion. So the pi bond goes to the bromine, lone pair from the bromine goes to one of those carbons, and the bromide's kicked off. Show this step as reversible. I'm okay with that. Or you can show it as irreversible, either one. And you get this bromonium. And then the water attacks the bromonium. It opens it up. And it opens it up on the less, it opens up on the more substituted side because this bromonium is not a perfect triangle. This carbon-bromine bond is much longer because it's already starting to leave, and it starts to leave the carbon that's best able to stabilize the developing delta positive charge. That's the more substituted side. And this is definitely irreversible right here. I think so. And then you have water. Take the breath out. That brings us to this step. Then we add this molecule, and we add a lot of it. if you see a sodium, please just get rid of it. Get rid of it. Gone, gone, gone. Just get rid of it. There are so many bad mechanisms that involve the sodium. A lot of people were doing this. No, sodium doesn't want electrons. A lot of people were doing this. No, sodium doesn't have a lone pair to do that with. Just get rid of it. It's an ionic compound. It dissociates into an anion form, which is the carbon side, and a cation form, which is the sodium side. The sodium is an Na+. If you really want to show a mechanism involving the sodium, then show this. Show that as a dissociation. If you really want to, but don't. There's no need to. Just show it as this carbanion. Okay, now it's tempting to say that taxobromine kicks that off, and then you have your product. But then why do we have this? That was your clue that something else is going on, especially since there's excess there. Thing is, this is a strong base. Acid-base reactions are far faster than SN1, SN2, E1, and E2 reactions are. It can just take that proton off. And then you have this. And before that, another one of those alkynes attacks, you have an intramolecular reaction that will beat out the intermolecular reaction with the alkyne. This intramolecular reaction, the neighboring group participation, is quite quick. That gives the epoxide. And the epoxide is what the alkyne, the acetylide, opens up. Acts as a nucleophile. And then this O- is protonated by the H3O+. Gives you that pattern. Okay, that's pretty much all I've got. There's practice exams. I'll have office hours on Saturday, and well, best wishes.